Okay, so now we're going to move on to a different kind of hypothesis testing. Um, so I know in the past, hypothesis testing tends to go hand in hand with the normal distribution. But in this case, it actually turns out to be a bit simpler. We're not going to use normal distribution at all. We're not really going to be talking about normal distribution. Hypothesis testing is independent of what you're testing it on. It's not a normal distribution thing. It can be used for other things. So in this sort of topic, we're going to be using it to test a hypothesis on whether or not a set of data is correlated or not correlated. So when you're doing normal distribution, your hypothesis tends to be about what is the mean or what is the standard deviation. Whereas here, we're going to be asking the question, is this set of data correlated? Or is it positively correlated? Is it negatively correlated? Let's do a hypothesis test to check if this is the case. Okay, and we'll see in a bit that it's not actually too difficult. It's just about a bit like with normal distribution hypothesis testing, you're mainly just setting out and saying the correct things and defining your terms correctly. And in fact, there's less calculation involved for the hypothesis testing on correlation. So that would be quite nice. To just get you started, this question I've come up with here, a bit of a thought experiment. You totally should be able to come up with an answer for this if you think about it in the right way. So consider, just to clarify what I mean here, if I randomly plot 2 points, any 2 points, they're pretty much always going to have perfect correlation, right? Unless it's a horizontal line. Because any 2 points make a line. So that, for instance, has a correlation or a PMCC of 1. I should clarify here, when I say 0 correlation, I mean a 0 PMCC. With 3 points, that would be a correlation of, or a PMCC of 1, whereas something like this would not be as good, so it'd be less than 1, it'd be closer to 0 perhaps. My question now is, can you come up with 5 specific points, so use coordinates, 5 specific pairs of, not pairs, but 5 specific coordinates which you think would have 0 correlation. If I put them in that calculator and found the PMCC on those 5 points, I would get 0 correlation. There's obviously infinite answers, but I just need one simple one. So see if you can come up with one, and then I'll give you one that I've come up with. If you find anything particularly interesting, you can put it in the chat. Okay, so 5 points. If you imagine a pattern, I'm just going to do it over here. You know how on a die you have the number 5 written like this? That, intuitively, it looks like it's got absolutely no correlation, right? Because no matter how you draw a line through it, it's almost rotationally symmetric, not perfectly, but there is a symmetry to it, which almost means that a line that was going positively and a line going negatively, neither one would be any better than the other. So it's almost like it's completely unsuitable for a linear regression. And in fact, if you check it on your calculator with some specific, sorry, just cut there for a moment. So if you check it on your calculator, the following specific 5 points will give you 0 correlation, and they are as follows. The points 0, 0, 0, 1, 0, minus 1. Oh, sorry, not quite 0, 1, is it? 1, 1, 1, minus 1, minus 1, 1, and minus 1, minus 1. Okay, that represents those 5 points. I've arbitrarily used 1 in this case, and there's 0 correlation. If you put those in your calculator, those 5, it would tell you that the R is 0. PMCC is 0. Cool. If you came up with something else even better than this, then do let me know. Okay, so before we get into the hypothesis testing of correlation, just a quick word on notation, a very brief one. For PMCC, we've got these two letters going on. Well, we've so far been using R, the letter R, but R is the PMCC of a sample, right? Which is why the calculator gives you an R, because whenever you put numbers into the calculator, it's assuming you're giving a sample of some data. Whereas if you consider that in practice, or not in practice, if you're taking the sample, you're presumably taking a sample of some greater thing, right? So for instance, I don't know, if you're measuring age and height of people, you're not going to measure the age and height of all people on Earth. So you're going to be doing a specific sample, and you'll get a PMCC, and you'll call that little r. If, however, you consider there must be some actual, correlation number, if indeed there is correlation, and the real number, so to speak, the one that you're trying to approximate, that we call rho, Greek letter rho, drawn a bit like a P, but without the sort of tail at the top. And this is just the PMCC of the population. Okay, it's a bit like, it's analogous to talking about a sample mean and a population mean. It's a bit like that. So it's a sample PMCC and a population PMCC. So when you, in a moment, we're going to start using these letters, R and rho. So just be aware that that's what they mean. Okay, cool. Okay, so let's talk about the actual thing. Hypothesis testing for zero correlation. I'll just talk through what the idea behind it is. So the idea is this. You want to know if two quantities are correlated, right? Let me think of a better example than usual. Let's say the quantity of CO2 in the atmosphere and average global temperature, something like this. Okay, so a sort of real world meaningful thing you want to check. Is there a correlation? And here are the steps you would do, simplified, is you would first make the hypothesis, and your default when you're doing correlation is, by default, your null is there is zero correlation, right? So you kind of go in blind, and it's up to you. The onus is on you as the scientist or the person collecting the data or analyzing it. The onus is on you to prove that there's a correlation. So by default there's none, and you then need to prove that there is one. So you first state that this is your hypothesis. You say, by default there's none, but I would like to see if there is in fact correlation. That's your alternative. And then you collect the data. And then once you've collected some data, some bivariate data, so in this case you've measured some global temperatures each year and also measured the CO2 level each year. You've got your data, you graph it, not by hand of course, you graph it and you calculate the PMCC. And then, we missed a step. Just before you calculate the PMCC, you also need to decide, just like with normal hypothesis testing, what is your significance level, right? So it'll be like a 1%, 5%, 10% kind of thing. Once you've done that, you'll look at your bivariate data, you will get a PMCC, and then you'll see, does that PMCC I've just calculated fall above or below a certain critical value, right? And it's that critical value for which it will effectively just be given to you. You're pretty much just going to be given what the critical value is, okay? And I'll talk about that in a moment. So you literally compare the PMCC to some number that you've been given. Is it less or is it more? And then you conclude either a null or an alternative. Okay, so I'm just going to sort of in note form just quickly summarize sort of the 4-step process here. but I'm not going to be technical about it yet. So this hypothesis testing for zero correlation is literally make a hypothesis, then you collect your data, then you calculate the PMCC, which in this case is your little r, and then you'll either accept or reject your hypothesis. Okay, this is the sort of high level overview of what we're going to do, but we'll get more specific in a moment, and we'll talk about R and rho and how we actually get the critical value. Okay, so much like with hypothesis testing, you still have this concept, much like normal distribution hypothesis testing, you still have this concept of one tail and two tail. Okay, and which one it is depends on how the hypothesis is phrased. Okay, or what you want to check is phrased. So if somebody said, I want to test if there is positive correlation between the amount of CO2 and the temperature and global temperature, is there a positive correlation between those two? That is a one-tail test, right? So let's say test for positive correlation of whatever. Okay, that's a one-tail test. If alternatively someone said, oh, I want to test if there's negative correlation, right? Obviously in this particular example we know there's no negative correlation, so in this case negative correlation would be saying that less CO2 would be causing more high temperatures, right? So it's still a correlation, but just in the other direction. This is also a one-tail test. Okay. So if you're testing for a specific type of correlation, then it's one tail. Okay. And in the next slide, when I talk about two tail, we'll see that quite naturally then two tail is when you don't care if it's positive or negative. You're just asking the question, is there correlation? That would be a two-tail test. Is there positive correlation? That question corresponds to a one-tail test. Is there negative correlation? That corresponds to a one-tail test. Okay, so I hope that's sort of clear. How we then lay it out mathematically, and now this is the bit where we talk about how we get our marks and how we do the proper procedure. So your null hypothesis, regardless of one tail or two tail, is always the same. You're going to write it like this: rho equals 0. Okay, I'm effectively just going to be teaching you what you need to be writing down. The null hypothesis is rho is 0, right? And remember, rho is the actual PMCC of the full population. Your alternative hypothesis, and then it depends on if you're testing for positive or negative. So you'll either write this, rho greater than 0, okay, or, right, you'll never write both of them, or you would write rho is less than 0, okay, and you would do the first one if your alternative hypothesis is that there's positive correlation, and you would write the second if your alternative hypothesis is that there's negative correlation. Okay, for our particular example of sort of climate change correlation, that would be a positive test. That's what we're checking for. Is there a positive correlation? What the actual number is doesn't matter, right? It just matters that it's not 0. If it's not 0, then we've shown that there's positive or negative correlation accordingly. Okay, so that's your setup for the one-tail test. What I'm now going to do is just double check we understand what the setup is for the two-tail test. Okay, so the two-tail test was answering the question, you know, is there is their correlation, just is their correlation. Positive or negative doesn't come into it. And in this case, our null, our default is that row is 0, and our alternative, any thoughts, will be that row, and this is always this, is not 0. Okay, for one tail, it'll be one or the other, less than or greater than. For two tail, it's just not 0. So that's your choice. Default is there's no correlation. Alternative, there is one, it's not 0. Okay, and that's it. That's the setup for two tail. So in the first instance, you'll be writing that down for a two tail, and for a one tail, you just have to decide if this symbol here is a less than or an equal to sign. Okay. Right, and then the next thing is we've done null hypothesis, we've written our alternative hypothesis, then we need to take note of two important values. So before you look at all these numbers on the slide, forget about that for a moment. You're going to take note of two things. You're going to take note of the significance level, which will usually be given to you, right? So two key parameters. And they are, number one, the significance level, which typically will be 1%, 2%, 5%, or whatever, example. And the second thing is the sample size, which we use the letter N to refer to. So the sample size that you used, or the amount of bivariate data you have, is going to influence your critical value. Okay. Now this part all starts to seem a little bit vague, and it kind of is. And the reason it's vague is because when it comes to correlation, the detailed statistics that underlie it are a bit too complicated to be taught at this level. So rather than do all that, you're just going to be given a table, and I'll talk about how to get this. You'll be given a table, and you'll literally say, this is my significance level, this is my sample size, and then you'll look up what the critical value is. Okay, just to remind you, with normal distribution, the critical value was something you calculated yourself. You took out your calculator and you said, all right, I want this particular area to be on the left or the right, and this is the mean, this is the standard deviation, what's my critical value? For correlation, you don't have to worry about any of that. Okay, so instead what you'll do is you'll find this table, and this table exists in the formula book. So towards the back of the standard formula book you'll get in an exam, there's all sorts of tables of numbers. Some are useful, some you'll never use. And the one you want to find has this heading, critical values for correlation coefficients, and you'll have this table of numbers here. Okay, this thing here, this Spearman's coefficient, we're not going to use that bit. Okay, so we're just using this bit, product moment coefficient. Okay, so if you read here, it explains what's going on. It says these tables concern tests of the hypothesis that a population correlation coefficient rho is 0. The values in the tables are the minimum values which need to be reached by a sample correlation coefficient in order to be significant at the level shown on a one-tailed test. Okay, so all that means is if it's a two-tailed test, you know what to do, right? You just halve it. You halve your significance. So a two-tailed test at 10% is exactly the same as a one-tailed test at 5%, and that's it. Okay, so really easy. So these are all the one-tailed test values. So you'll find these in your formula book. I'm going to put a link to the digital version of the formula book in the description of this video, so you can look it up and then you can find it. Make the effort to find it yourself. because I think it's good to have the practice to have actually seen it and where it is in the book, because there's so many tables back there. It's easy to get a bit lost in what you're actually trying to find. So find that in the book, and then you can see you've got this. And let's say my sample size was 10 and my significance level was 2.5%. So I'd look at, okay, sample size is 10, 2.5% if it's one tail, and I mean, you know how to look up things in a table. There it is, 0.6319. This is my critical value. Okay. And that's the number I'm going to compare to my actual sample PMCC, my little r. So if the little r is less than this, it's closer to the 0, then we go with the null hypothesis. If the little r is much bigger, in this case, we'll go with the alternate hypothesis. Okay. So let's take a look at some examples, I think, to just hone this down. Okay, so we've got the first of two examples. A scientist takes 30 observations, n equals 30, of the masses of two reactants in an experiment. That's our bivariate data. She calculates a PMCC correlation coefficient of r equals minus 0.45. Okay, so that's our sample PMCC. The scientist believes there is no correlation between the masses of the two reactants. Test at the 10% level of significance, the scientists claim, stating your hypotheses clearly. Okay, so first of all, believes there is no correlation. Now, it doesn't actually matter if she believes there's no correlation or there is correlation. That's not what's important. The only thing that's important is, does she think there's no correlation, or there's no positive correlation, or there's no negative correlation? In this case, it's unspecified. So this wording tells me that it's two-tail. Okay, if you see the word positive or negative there, then you know that it's a one-tail. So this is two-tail. Therefore, my significance level, and I'm going to call this the one-tail significance level, is 5%, right? Because the 10% is the two-tail, divide by 2, my one-tail is 5%. And then let's state our hypotheses. So H0, in this case, is always rho equals 0, and my alternative is rho is not 0. And then you go to the table. So the critical value for n equals 30 and a significance level of 5%, which is 0.05. If you look that up in the table, and I suggest you do to confirm this makes sense, is 0.3061 apparently. I'm going from the textbooks on this, so hopefully that is the case. So that's the significance level. Remember, this is two-tail, so my critical region, okay, my critical region is going to be anything that's more extreme on either side of 0.3061. And in this case, by extreme, we mean further and further away from the null hypothesis, which is 0. So the critical region is if we get an R that's bigger than 0.3061, or an R that's less than the negative of that, and that's the other tail. Okay. Remember, correlation is always from -1 to 1. And then this critical region is sort of at the tail end of that interval on the two tails. So that's our critical region. And then we look at our observed value, which is -0.45. and then we'd say minus 0.45. Well, that's even more extreme. That's less than minus 0.3061. Okay, so therefore we reject H0. Okay, because that's a significant correlation, minus 0.45. It's a significant negative correlation. So then we would conclude in a final sentence, there is evidence, okay, and you want to phrase it that way, there is evidence that at the 10% level, and remember your evidence is dependent on your significance level, that at the 10% level there is a correlation, and then probably finish that off and say between, and then talk about the reality of the situation between the masses of the two reactants. Okay, and that's it. It's really similar to normal distribution. The main sort of weirdness is in how this critical region is decided, which for your purposes is going to be looking up a number in a table. Okay, let's just do one more of these and then I'll give you some time for questions. Okay, the table from the large data set shows the daily maximum gust X and the daily maximum relative humidity Y in Leeming for a sample of 8 days. Find the PMCC coefficient for these data. Okay, so that's easy. That's literally, do you know how to use a calculator? You can always check if you're able to do that. I think we've probably done it enough times now, actually. And then part A, if I look that up, should be 0.1149. What is important though is what should I label this as, R or rho? And in this case I hope you're satisfied that this is an R because this is a sample. So R is 0.1149, and then B, now let me do the hypothesis test. Test at the 10% level of significance whether there is evidence of a positive correlation between the two things. State your hypotheses clearly. Okay, is there evidence of positive correlation? So now we're talking one tail, right? Because the word positive was dropped here. So it's a one tail test. Our H0 is, as always, rho equals 0. And our alternative is, if we think it's positive, potentially, rho is greater than 0. Okay. Significance level is 10%. And we don't have to change it. We don't have to halve it because it's one tail. That's 0.1. What is our N, the sample size? Well, we've got 8 days. So it's 8. So then from that we get a critical value, and now we have to go to the table in the formula book and we look up, right, significance level 0.1, N equals 8, what value do I get? And apparently it's 0.5067. Okay, so then what's my critical region? It's one tail, so it's just one range, and it's whatever is more extreme than that. So it's when R is greater than 0.5067. Then we look at what was the R we got. It was 0.1149, which is actually very close to 0, so it's not very significant. 0.1149 is actually much less rather than greater, much less than 0.5067. So then we would say not sufficient evidence to reject H0. Okay. And then you write your final English sentence. Final English sentence here. Okay. and I'll just read out what that should be from the particular example so you can get an idea. You then want to write something like, there is not sufficient evidence at the 10% level of significance of a positive correlation between the daily maximum gust and the daily maximum relative humidity. That's what you then want to write at the end. And you just want to hit all the key points of the fact that it's not sufficient evidence. Don't ever say there is no correlation. We don't know that. Maybe there is. It's just the data we've got was not. We've got unlucky, right? So there's not sufficient evidence. Mention the significance level. Mention that you were testing for positive rather than generic, unspecified correlation. Okay, and that's it. Other than that, I don't think it's too complicated, really. These are quite easy marks to get, so definitely worth investing some time into learning. Let's take a look at some questions for you to try yourself. Okay, so I think I've got 3 or maybe 4 questions, actually. 3 slides, so that must be 4 questions. Because of the nature of the topic, the answers are all going to be very similar, but the key is in the subtleties. So are you doing one tail and two tail correctly, and are you writing the correct wording down? Hopefully looking things up in the table itself will be something you're not really getting wrong. But put a genuine effort into writing up full answers to this, because if you can write out a full perfect hypothesis test answer, and you look in the back of the textbook to check it, and you've got it right, then you know you're on the right track. You don't want to just glance at the back and think, oh, I know what the numbers are, I roughly get the process. Because if you haven't practiced it a couple of times, you might not realize which words you're missing, or which small errors you might be making. So do give it a go. Yeah, I'll pause the video now, have a go at these 2, and then there'll be a couple more after. Okay, so penultimate question. See if you can do a hypothesis test on this one. And finally, just try this one as well.